very much, Roberto. Okay, so it's a shift from the rather engaging last performance. My topic is about something I'm starting to learn a little bit about. I will cover the questions. I have an expert informant. Then I'll give you an introduction to parametric design and generative design. Ask some questions about the difference between that and sketching and where creativity comes in all of this. So I'm starting a research project at the Bartlett School of Architecture where I'm visiting for part of this year and part of next year. I'm not an architect. It's part of University College London. Architects are really interesting people, especially how creative they are and how closely connected they are to the equipment they use, this digital software that they use. It's a very close relation they bear to their tools. So that topic of how the tools affect the way we think is something I'm really interested in. And in the case of architects, they're using new tools, amazing new tools, which I'll tell you a little bit about. And these tools are changing both architecture and how architects go about thinking. I think that the topic of what is thought and how people think is an interesting one to explore because historically we've always assumed, as was said just earlier today, that thinking is propositional, operations on propositions. But we do know that we certainly can think visually, we can think musically or auditorily, gustatorily, olfactory, the perfumers, and certainly dancers and choreographers, they think with their bodies. So there is an opportunity to explore more broadly what thinking is, and we need new conceptions of how to go about understanding what thinking is, and I like to think of that as the microstructure of thinking. So sketching has a role in that, and then the problem of what are the digital sketches, what role do those play in thinking, and how is all this idea of sketching changing with software. Architects, they sketch with tools, with digital tools. That's what they do. And we do. That's how we broadcast them to each other. So here's a classic architect, and there's no fewer 3D models. You go to the architecture school, every place is chock-a-block with the 3D models. So everybody's generating them. They're all sorts. These are called a sketch model. So it's an early model you make before you have specifics, just to get an idea. And it could be in cardboard, it could be in paper, it could be from folded foam core that they make. You can have sketch models on sketched in 2 dimensions, like that. And these are similar to conceptual models. Early conceptual models, before you really know, these are early kinds, but these are blocky. These ones are also sometimes called mass models, where you just sort of drape cloth over the whole thing and say, what does it look like from a mass point of view? And now this is what you get when you go into one of the tools. This is how you sketch in the tools, in parametric modeling, where you put, this is a visual programming language, and you say, okay, I'm going to make a line, and then you say, okay, I'm just going to drag down a line, and then let me connect it to its X and Y size, and that's how they connect them all together. Most of them don't program with programming, but this is a programming language, and they see the effect immediately on the other side, and they can change the numbers in there, and it changes, and they see how it works like that. Now, Martha Scara is one of my experts, and she's a partner at Foster's. She's really excellent at what she does. She's been teaching generative design at the Bartlett for over 10 years now, 12 years, and currently she's doing some great work. The Mexico City Airport, I don't know, $5 or $10 billion building, amazing building. That's the one that she came up with. So at Foster, so she's doing very well, and she's got a whole team, and it's quite interesting. So I asked Martha questions, but we haven't had that much time together yet, so this is really early stuff for me. In generative design, they always use optimization. I'll explain it in a minute. But how do you do it if you don't use optimization? That's a question I want to ask her, and I'll explain that better. in a minute. So really, what I wanted to know was, what's the role of sketching in generative design? If this is what they are working in, and they go to this straight away, it takes them about 30 minutes to build one of these things, just even a quick one, maybe 15 or 20 minutes, but anything of interest take 30, 60 minutes. And then you get this enormous power. But how can you think slowly to do it in this way when, you know, you like to write quickly and so on? So that's the question that I have. And the reason I'm talking about generative design is because this is what's happening in life. This is what's changing now. Oh, sound.
By the designer. And from those options, pick the one design that delivers on the most important.
Sorry, I'm going to start it from the beginning.
Design you couldn't possibly have imagined.
Okay.
This is generative design, a technology that harnesses massive computing power, creating forms with precise amounts of material only when needed, achieving maximum performance while wasting nothing. But generative design can be about much more than simply turning out alternatives. Prototypes can be scanned and equipped with sensors that provide real-time performance data that can be looped back into the design process, so the object, in effect, co-designs itself. And depending on the material and method of manufacture chosen, the software can optimize the design for those choices. In its search for the optimal design, generative design creates complex forms that would otherwise be impossible to make using traditional manufacturing methods. Now, with advancements in material science and the ability of 3D printers to print metal, companies like Airbus can create forms like this airplane partition panel that's half as light and just as strong. The result? Significant reduction in fuel costs and CO2 emissions. The things that have limited us in the past, software, materials, manufacturing, no longer do so. With generative design, the world can look and perform any way we want it to. This is the next stage in the evolution of design, and it's happening now.
So I'm working with Autodesk, when I heard about this tool, I couldn't believe it. I don't know whether you were able to hear, but they 3D print in steel, in metal. So you can 3D print in anything almost now, and they even do it in biological things. So you can have the form, and you have to have it in an appropriate manner that you can press the button and it converts it to the language for the printer, but obviously you can't get that from hand sketching. So you can see the forces are driving everything in this direction, and then you can minimize the weight of things, and it peels it back and takes away everything because it has material analysis built into the system. So there's optimization along so many things: weight, strength, temperature support. All these are optimizations, and that's what's happening. So Dreamcatcher, which is the name of that program, it was a project, but now they're starting to roll it out as a product soon. It uses algorithms and AI reasoning, and it generates thousands of designs. And then it performs a performance analysis on each of the designs. It asks, okay, how much is this way? But you tell it what you care about. But then, so you specify the goals and your constraints, and then the computer generates on the basis of those. So it combines the human ideas about what you want and what's good with the computational artificial intelligence of what's good, and you get this combination working together, and it's in the clouds, so there's like thousands of computers that are working on this. It could take 30 minutes to generate, well, thousands of designs, so it could take a while. But, and then you straight away 3D print a prototype, and then you go back and say, no, I have to change it in the following way. And then the system, because people are using the cloud, they collect the good cases of intermediate results and so on, and those become cases that when someone else wants to build something with a part like this, it says, oh, I built a part like that before, and now it starts to consider those as early starting points in the search. Changing design, yes? I mean, you can imagine what this does for product design. So I want to tell you now a little bit about parametric design, and then I've told you a tiny bit about generative design, and then I want to ask some questions about sketching and the strength of each of these. So,
parametric modeling software incorporates programming techniques into the design process.
so look at their
This integration
folding.
allows for new forms to be generated at a fast pace that otherwise couldn't be.
So this is a parameter, and they just change the parameter folding, and they get, from an ordinary column, they get these complex things that have sort of inner folds
Parametric software allows the user to generate variants on the same design in real time by changing the input into the programmatic part of the software. It can now be said this is a shift from mass production into mass customization. So how does this relate to architecture? By applying conditions to the programmatic script, you can generate designs that accommodate the different variants, for example occupancy, use and light conditions.
so we'd fix the size of the room.
To see the alterations in real time and allow the architect to pick a complex form that otherwise may not have been thought about due to the complexity of the design. Modern examples of parametrically designed architecture includes Beijing National Stadium by Herzog and de Meuron, Guangzhou Opera by Zaha Hadid Architect, Yas Hotel by Asymptote. None of these previous examples would have been able to be designed or manufactured without parametric software.
And
so what does this mean for the future of
this
architecture?
is what they look like.
It is clear that a balance between that which is designed by and on computers and that which is hand-drawn must be struck in order to communicate ideas effectively while still continuing to design complex forms. With this being said, it's worrying to think that with parametric software, the architect can become more of an inputter of numbers rather than always a designer in the traditional sense.
Okay, so they were concerned about the same question, about the role of human creativity without hand drawing and the loss of that in architecture when you're manipulating and pulling levers and stuff. And generative design, so just to come back and tell you a little more about how parametric works, you'd start with, you drag down like in Photoshop or something else, some things you want like points or lines, but anything else can often be defined in terms of it. So you could start with a point and say, I want a line, and just make it go forward. And that's an operation on a point. And what you do is you take these things and you perform operations. And because they have these, crazy operations now, and people build new modules that you plug in and they perform new operations, such as folding. Here's a column. I want you to fold it on the x-axis, fold it on the y-axis, and you're folding it inside, and then you produce those crazy columns. You never would have guessed anything could have come out of folding like that. Then you can, and people invent new operations. You get shapes that you never dreamt of before. So you define these relationships, and then they multiply things. So I asked Martha to, because I've worked with the Dreamcatcher product, and that's mostly for product design, but it's coming for architecture eventually. And there you say, okay, I want a chair. And if you wanted to design a chair, you wouldn't say much. You'd say, okay, if the chair, the space of the chair is going to be like a column. I'm just going to tell you, it occupies this space. I'm not telling you anything more about it. And it's got to have force at about this height that'll handle enough, say, 200 kilograms. Okay? Enough force up there. And maybe I want a back, maybe I don't want a back. I'll specify if the back has got to push back on you. And it connects the back, maybe a connector, or it's either a solid piece or it's a connector if it wobbles. That's all I tell it. I don't tell it it needs legs. Yeah.
Just a question, but you can change parameters only with the
Slider.
CP, but also
The slider.
okay.
You have lots of
Okay,
sliders. Yeah, they can do lots of different ways of doing it. In fact, I was going to show you one thing where now the next thing that people are doing is Oculus Rift. It's a virtual reality. So what you do then is you walk around and the sliders are in the world. I want it this big. and now you say it like that rather than do it that way. So the input space is changing. It's happening fast. It's amazingly fast. But coming back to the dream catcher, so that's all I tell it. And then it starts to come up with possible seeds and possible ways of supporting it. I mean, crazy, wonderful, amazing ways of supporting it. And it generates thousands. And then you start to look at them. You say, I like that one, I like that one, I like that one, I don't like that, I don't like that. Now what it can't do is marry them. Say, I like that, marry those two. That'll happen in the future. It can't do that yet. But you know that that's what they're going to do in the future. They like this genetic algorithm stuff. So that's how generative design works in Dreamcatcher. So I know that the way they teach it in school is by saying you have to do all this optimization. And, well, what's the optimization on this? I can tell it, optimize it for weight or something, or strength. But how do I get interesting shapes from just standard optimization in the way they do it normally, not in Dreamcatcher? So I asked Martha, look, make an interesting chair. And then I thought, oh, well, I'm not going to tell you about the chair, but let's do a desk, a small table, because that's basically a chair with, a small table is a chair, and with the back is the chair. So, so I asked her to do that, and she says, okay, well, look, what are we doing? Where's the, why is it duplicating? It must be the, she said, okay, well, look, we're going to specify a bunch of relations, and then we're going to choose some relations as important. So here, I might choose the distance between the legs as important, a parameter that I could change, or the distance there, the distance there. I could choose the width of the leg as important. And now I could ask it to generate in this space. I've given it no optimization yet. I'm just saying, let's look at possibilities. And we can hold some things fixed, or we could not hold things fixed. And the surprising thing about this is that when you ask it to do that, it can come out with outcomes that are amazingly different. So here I did this. I mean, I was just thinking about it myself. So I could have essentially, there are 4 legs here, right? But I changed the width until finally they hit each other. And it produces the equivalent of 2 legs, like that. Over here, if I had if I didn't just control the distance from the end, the corners, I controlled the distance of the corner and I controlled the distance at the bottom, then if I can allow the bottom to go negative, I can have them cross over. So you can get crossovers. I can get single leg in the center, and I can get all these combinations and many combinations that are completely not what you would be expecting when you start with 4 legs. So this is how you can generate interesting design. Now, you don't get one of these. So there are lots of chairs you're not going to get. Lots of chairs you're not going to get. But you do get a surprising number of chairs. All right. How am I doing for time? Sorry. My timer was off. I can't get it on. Okay. Sorry. Black cursor on black screen. No. Fine. So here is how they use it in class. I'm going to introduce this so that I can eventually try to create the context for you to understand what's happening and why this is a challenge for sketching. And the role of these digital sketches and what they call sketch models, those parameter things. Because they are just, after all, still a kind of sketch, right? So here's what you would get in a typical architectural class in, say, taking a class in generative. Say, your job is to design a roof with the following dimensions, and they give you the site, too. So these are roofs that you've seen, and we want to design a roof. This is really a standard thing that they do. So in the old days meaning 10 years ago, you'd start with a pencil for a few minutes, you'd design some shapes, and then you would take out a good 3D modeling program and you design what you want in the 3D modeling program. Oh, that's in here. Now, what you would do is you'd go into your modeling program without doing the sketching, and you would put the parameters together, tie them up the way you want, and then with something like this, you can manipulate it and it changes the shape over there in accordance with these. So now you can introduce any shape in X and Y that you would like. The newer school, you specify some properties of the surface you want to optimize, and now you say, well, I wanted this roof. I wanted to perform well under high wind. I wanted to do well under snow, or take the rain off, or I wanted to reflect heat effectively. And now the system starts to convert these into a goodness function, and so it will then take a parametric surface, it'll design a parametrics, choose one with different numbers, substituting in different numbers, and each time it gives you a shape, it calculates how good it is. And that's a big change, because before you had to build the shape yourself and calculate the goodness. Now it's doing it in the background, so it's only showing you the shapes that are the good ones with respect to these parameters. So imagine all the work it's doing for you now. And this is what it would happen. So they'll use all these different physical things are built right into the programs now as little modules that you plug in. So here's fluid dynamics, and they're going to use fluid dynamics to generate interesting candidates. So first you'll notice that you can watch it, and this is what's happening. These are different methods for doing it. The second optimization method. And this is what they would do by the end of the class, the end of the course. They would be able to design a roof for these things. And the surprising thing, of course, is that roofs now don't look like roofs used to. Right? You just don't look like. You saw what the Yaz building was like. You saw the other buildings. The roofs are completely different. So that's how you would use it, and it's performing these analyses underneath. These are all dynamic animated sketches, yeah? But how you create the sketch was not with your hand. It's interesting because creativity usually is treated as substantially in the generative phase, where you're coming up with interesting candidates. And then you prune or selectively choose the ones, and you learn from the outcome, and then you try to feed back into the generation phase again. So these ways, by exploring the space so massively, they are not constrained by the past. They're always, reframing the question. And because they search the space so largely, so effectively, you get a big separation between the candidates that are being considered, whereas humans do not usually search extremely far apart. They may individuals go there, this individual goes there, but you don't get such a sampling that's so far apart. And you can benefit from randomness. And so now the system generates these interesting candidate structures that could be completely counterintuitive. And it's powerful because we can use the property that we would normally use after in the process itself, beforehand. So that changes a lot. And these are the kind of structures that you get nowadays. Here's another one. Somebody says, I want you to design an office for a certain number of people, and I'm going to give you the dimensions. Now minimize the heat or loss. If you had done it in the old days, if it were me, I would look at dozens of cases of interesting office design or building design for these offices, and that would be the basis for me to start thinking about something new, or I would look for inspiration from other places. But the alternative is to tell it the basic specs, the constraints, and tell it to go wild and generate. And what you get now is buildings. So I'm trying to minimize the heat signature in this building. And I'm saying preserve the volume, and now tell me all the shapes, given where the sun comes like this and the temperature across the entire year. Tell me, cook that all into one function, and now tell me some of the shapes that optimize it, and you end up with a shape you never would have thought of, right? But this is going to be optimal with respect to energy consumption, the amount of air conditioning you need, or the amount of heating you need. Usually it's air conditioning. And there are just so many plugins that you can now perform on these sorts of things. So you can ask, where's the human creativity? Now, this is a very early Frank Gehry sketch for the Louis Vuitton building. I'd like to see it, I think. I started to look at the dates. So he did the sketch in 2006, and they built it by 2014. This is what the building looks like. This was his early sketch. Pretty good, huh? This is the IAC building, one of the famous buildings he did early in New York. Now, he did the sketch in 1993. This is the building built in 2007. That's
Did you make it on a notebook?
a moleskin notebook. Bigger. So Gehry, everybody used to say Gehry gets his ideas by crumpling paper. He denies it. He denies it. So he doesn't.
He denies it.
He denies it. But, people have said, see the one in the basket there? He denies it. So he has this characteristic way of sketching, and you think that he's sort of solving some ideas or coming up with intuitions in sketching like this. So there's that, the old one, or there's this. Do they really start there? So when I asked Martha to do the chair, and then I said, well, how do you get all the chairs? And I said, what about all those other kinds of legs? And then she said, oh, well, I'll use negatives. So then she explained it to me using this, how she would basically code the other one. But she wanted to code it straight away. She would just, a chair is easy, I'll just start with 4 legs. Now, maybe that's the wrong way to code it, right? And maybe, you'll never get these ones like that. So, but she started with that, and she's, when we talked about crossovers, and she said, well, So she made little sketches, but I think that was more for my sake than for her sake. Well, where's the power of this? So if you ask, okay, so sketching on paper is 2D plus projections. So here is what you learn to do. And by the way, the people who are the very best at these are dentists. Because dentists have to think about the 3 dimensions, the different faces on teeth. They bill you by the number of faces on your teeth. Yeah, I talk to them how they bill, this is 6 sides, and you're putting an extra side in there. $20 a side,
So they those the mental rotation test?
I don't know what any tests on that have been for dentists, but I know that they have to do this, and the place where they test it before you go to school is in dentistry to see how good they are in these projections. But you'll notice that this is what they are. You get this one and you get that one, and you have to be able to put those 2 together to come up a shape like that. That's not so easy, right? You could have inconsistencies where, in fact, you try to put the projections together and they're incorrect. So errors can creep into there. So I would like to think of these multiple projections as an inexplicit way of showing that. And you really want a 3D shape, especially when you could rotate. That would be a much more explicit thing, where now interactivity is part of your relation to the object. And so the parametric model is a true 3-dimensional model. So right away, you've got a big bonus by going to a parametric or a 3D modeling over a hand sketch. It gives you honest 3D, and you're not going to make mistakes. The interactivity allows you to look from any angle. Well, that's certainly a powerful thing. And where people can make mistakes in unifying them, they won't make a mistake because it's completely explicitly, the 3D in a two-dimensional model is not explicitly represented, but the 3D in a 3D model is explicitly represented. And then as before, you get the complexity. Okay, I was just going to show you that video from before of the columns. So the parametric model handles those massive complexity. And then how do you cope with complexity? So then these modern buildings are so complicated, you can't build them any longer the old way. You know, they're so big, some of them, and they have so many parts, and you want to ensure consistency with the HVAC system and with the electrical wiring and with everything. You have to have a different way of dealing with it. But so you suppose you've said, well, I want to shrink this. This is the Gherkin, the one in London. Suppose I want to shrink it. Well, if you did that by hand, there's so many dependencies that if you shrink it, you'd have to calculate so many things. But in the case of these 3D software, you say, hold all these things constant, now just change the radius. And it will hold them constant, and you'll be able to explore the possibilities. So the interactivity is massive. When I talked to the people who are all the teachers of generative, they were very keen to say, well, look, you get a much deeper understanding of the structure this way. So to take an early case of one of the early teachers, he was working with Anthony Gormley. So Anthony Gormley makes sculptures like this. And Gormley asked him, so Gormley's sculptures, these are some of his sculptures. He's a guy obsessed with his own form, but he, tends to produce it in wire. And the question was, how do I take a shape like this and put wires coming out of it? Because the wire is going to hit my arm. I can't have, he wanted to have, like the Michelin Man. He wanted to just inflate himself out and just have that with wires so that you'd see the body on the inside and then you see the bigger version on the outside with wires. Not so easy. It should be easy, but of course the Michelin Man can't be there. The arm comes this way, this goes that way. They're going to clash. They're going to hit each other. So how do you figure out how to do that? Well, you have to resort to mathematics. You have to start thinking, conceptualizing it as a problem in math. How can you have surface normals? I mean, should they be surface normals? The ones that come out, 90 degrees to the body, like all of that. So when he started working on this generative guy, it turned out to be counterintuitive. All the ordinary or simple methods he tried, they weren't working. And he had to understand the problem in a much deeper way until he found a method of doing it. I don't know if it was Voronoi spaces or not. I don't know if you know those. But there are various sorts of mathematical things that you could try. And the result was he did find an answer, and it gave a much deeper understanding of the nature of that problem. So here we have this again, the folding ratio. You get a much deeper understanding of the problem, and you can now characterize what's common between these things that look completely different. Turns out to be just one parameter in this abstract space, which means that you can now generalize and characterize structure. We understand science through generalization. We want to find the deep rules, simple rules that govern the multiplicity of phenomena. So if you can reduce it to a small set of rules, you can understand it better. You can see the possibilities. And that's what they're doing. Well, what happened to the basic simple sketch? People didn't search through sketching for understanding. They might have, but you have to sketch a lot in order to see that, oh, these are all parameters, basically changes in parameters. It's a mathematization of this exploration now. So what's happening? What's the role of sketching if our conception of what we're looking for is being changed? And then there's this problem. I ask you, arrange the furniture in your flat, okay? You're going to go out and buy furniture. We've given you this set of furniture. Arrange the furniture. Well, if you do it on a sketch, every time you change a piece, you have to have a new sketch. It would be much better to use a piece of software or to cut it out in two-dimensional paper and lay it out on a piece of paper like that, or in 3 dimensions, cut out pieces, make pieces, and move them around like that. So if that's the case, you can go paper or digital. If the furniture pieces are invariant, each rearrangement is a different 2D sketch. That's a bad idea. So the better solutions are all going to involve either physical models with paper or digital models that you can manipulate the same way because you can just drag them around. Or you could even identify principles like, I want to preserve the maximum space. Okay, stay on the walls and give me the maximum space conceptualized as free space, and let it generate possibilities for you. You'll come up with some very interesting answers. Sketching is not going to be your vehicle of choice there. So we seem to have a lot of arguments for the automatic methods, or well, what can we say for sketching? So sketching formalisms, like perspective, they still do enforce a certain discipline, namely, perspective and such a thing. You have to put them in that, and that forces you to think in a certain way. And more importantly, sketching causes greater attention to proportion, details, and scale that people are interested in. So I can define the chair as a set of parameters, but I haven't really understood the nature of the appearance of the relation between the scale. So if I specify I want the back to be the same height as the base, that may look good in certain sizes, but as it gets better, it doesn't look good. So your concern with scale and proportionality is a very human thing, and sketching allows you to explore that space in a way in which you might not explore it at all with parameters, because you don't have that kind of control. You're not exploring it in the same way. And sketching is an interactive strategy for creating new ideas. That is the one that we are quite familiar with, so I want to explore some of that. So sketching is an interactive strategy. So I'm going to explore many of these in a second. So intuitively, when you think I'm trying to sketch something, I have some idea. I'm going to say, okay, I want you to design a chair. Again, we'll stay with the chair. So, you think here, before you come to the piece of paper, you have some ideas what you're interested in doing. But when you get to the paper, something changes. So you have some ideas, you're imagining some possibilities, but probably not to the resolution that you will have when you're at the paper. And when you're at the paper, I just made this stroke. How do I continue from this stroke to conform to my imagination in some way? That's always a problem. So you begin to sketch, and then you might also feel the dynamics of your own movement. And thinking of yesterday's calligraphy case, I'll give you an example of that. So then, as you sketch, you may see new properties that you like. So you're moving in a very quick, dynamic way, saying, oh yeah, let me elaborate that, or let me constrain that. Then projection is the property where you can look at something. I would say, okay, now imagine this cup half full, and your ability to have a mental image and put it on something external is projection. It's been understudied. It's practically not studied at all, as a matter of fact. I think it's really central to human cognition and possibly distinguishes us from animals, but maybe animals do it too. And this capacity to have a mental image of our own construct and to put it into the world, to see what the superposition is like, that's a very central thing. So a natural interactive strategy is you superimpose on the world, and then you create the thing you just thought you were going to create. All right, so now here is the feeling of the properties. Now you can see the weight. Surely the calligraphy and the nature of this. This is Japanese. You know, it's all about weight and movement. So that's got to be some component of a curve. You know, I could do the curve like this, but I do the curve like that in order to get the dynamics of the curve. And that's going to be something that is embodied. You won't have through parametric. The feel of something is what you're trying to get into the building, for instance. Then there is the problem of there is the opportunity of perceptual surprise, the phenomenon. So, so which shapes can you see here? Do you see those shapes? You're free to sort of see it any way you like. You could see it as three lines crossing over each other, maybe one underneath, one below, any way you like to see that. Or you could pull them apart, you could see it in this space, that space, that space, that space. Or you could pull them apart like that. So they're ambiguous, how you see them. Relentlessly ambiguous. So this is a property that is counted on in using sketching for creativity. This is nothing new, I believe. So what do you see here? I mean, how diverse are the visions that people have of this one sketch? All of it could be a source of creativity. So one way of thinking of this is that there are multiple semantics. There are many versions of what is there to be seen, and you could, if you distinguish the presence of vertices, a vertex as an entity, you could see it there. Or if you identify patterns as ontological things, you can see them there. They're not given what the semantics are. And then there are many kinds of ways you can, this is negative space, right? Where, in fact, just the black bits are there, but you see them as an E. So now things that aren't there are getting definition. The semantics of how you see things are changing. So that's under constraint. Can we do that in parametric models? Or here, this is I just appreciated that this is analog computation of parametric designs. So this is the famous Darcy Thompson stuff, where Darcy Thompson, many of you must know him. He was a great polymath. He was a professor of 4 different fields at Cambridge. And he did math and biology. And this was kind of his counterexample to evolution, because evolution sort of assumes that it doesn't require it, but that the causes of these changes would be genetic causes. But he was very keen on looking at the importance of development. So you could have the same genetic basis, but when this was a little fish, if you fed it in a certain way, it might come out like this, like a foie gras. If you fed it too much. Yeah. So, but his genius was to mathematize it and say, oh, let me look at the operations that I can perform on a geometric surface. I can shear it, I can rotate it, I can stretch it, dilate it, I can do various operations. And now let me perform that on this rubber sheet, and I can produce these different creatures. So that is one way that people have of playing with, the physically playing with. So Gary crumples the paper, not. And you could crumple the fish to get ideas. But they can do that parametrically. So these are different ways that, in fact, architects in the old days do work with diagrams. They used to rotate them, they would occlude parts of them, they'd stretch them, they'd move their heads, they'd come in like this. These are all embodied actions that they perform with respect to the sketch. And here we have, if you interact with something, you often see it in a new way. So I'm going to go through a sequence very quickly, and please just call out what shape this is. What shape is this? Call- Okay, you got the idea quickly. Oh. Okay. So when do you reclassify the square as a diamond? By interacting with it, you know, by manipulating it, I made a square into a diamond. But it was a square, right? I mean, but it's a diamond now, but all right. So, and now what about reverse? When do you classify the diamond as a square? Right? Is it going to be at the last? You went square, 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 diamond. Now do you go diamond square, or do you go diamond, diamond, square? All right, so there even the directionality changes how you are going to register it as a thing, what it is, the thing that it is. So sketching is a way of self-stimulation. It's a provocation to the self. And my conclusions are, parametric design is a necessary part of modern architectural design, and that's because of the complexity and the size of the new architectures and because of the possibilities of technology. Sorry. Generative design allows us to optimize parameters like meeting these needs, which we couldn't get from sketching before. We had to still compute them, and we couldn't do it. We didn't know how. And so we're getting a new mathematical basis and a new understanding of the very structures that we're making. But what do we lose? So we don't have the interactive control of imagination because we're just choosing the things we like. You can use sliders and look at them and then slide them in directions. So that's more like interactive sketching. But we don't have any physical feeling of our designs. We 3D print them and we get that sense for what they are, but we don't have the physical feeling in making it. And we don't seem to get the self-provocation in the intermediate unless a slider acts like that. So the real question I have is, will we discover analogous interactive strategies in generative and parametric design that will make those methods, in some sense, give us the same facilities that we have through manual sketching, through hand sketching? That's it.